Imagine stepping onto a spacecraft, pressing a button, and arriving at a star system 4 light-years away before your morning coffee gets cold. For decades, this dream has lived only in science fiction. But here's the twist. Some of the brightest minds in physics are now saying it might not be impossible. The question isn't just, can we do it anymore? It's, how soon can we figure this out? Today, we're diving deep into one of humanity's most ambitious questions. Will faster-than-light travel ever be possible? And one quick question. If you could instantly travel to any place in the universe, where would you go first? Let me know in the comments. I will pin the most creative answer. Now let's begin. Let's start with something that might surprise you. Einstein didn't say nothing could move faster than light. He said nothing could move through space faster than light. There's a loophole here, and it's been hiding in plain sight for over a century. Space itself isn't bound by the same rules that govern matter and energy. Space can expand, contract, and warp in ways that seem to violate our everyday intuitions. In fact, space is doing this right now. The universe itself is expanding, and distant galaxies are moving away from us faster than light, not because they're zooming through space at impossible speeds, but because the space between us and them is stretching. This distinction is absolutely crucial. It means that if we could somehow manipulate space itself, we might be able to travel vast distances without ever technically breaking the speed of light. This brings us to the warp drive, a concept that sounds like pure fantasy but is rooted in genuine physics. The idea was first formalized in 1994 by a Mexican physicist named Miguel Alcubierre. He was inspired by Star Trek, but instead of just daydreaming, he sat down and worked through Einstein's field equations to see if such a thing could exist mathematically. What he discovered was remarkable. Alcubierre showed that you could, in theory, create a bubble of warped space around a spacecraft. This bubble would contract space in front of the ship and expand it behind the ship. The vessel itself wouldn't move through space at all. Instead, it would ride a wave of distorted space-time like a surfer riding an ocean wave. Inside the bubble, you'd feel nothing. No acceleration, no crushing forces, just smooth sailing, while the universe rushes past you at speeds that would make light itself jealous. Now, before you start packing your bags for Alpha Centauri, there's a catch. Actually, there are several catches, and they're significant. The original Alcubierre Drive required something called exotic matter. This isn't the kind of matter you'll find on the periodic table. Exotic matter would need to have negative mass or negative energy density, which means it would repel rather than attract under gravity. To put it bluntly, we've never observed anything like this in nature. Some physicists argue it might not even exist. Others point to certain quantum effects like the Casimir effect as potential hints that negative energy might be possible under very specific conditions. But even if it exists, the amount required was initially estimated to be absurdly large. We're talking about the mass energy equivalent of Jupiter, or in some calculations, even more. That's obviously not practical. You can't carry a Jupiter-sized fuel tank. This is where things start to get really fascinating. Over the past 3 decades, scientists haven't given up. Instead, they've been refining the concept, finding clever ways to reduce the energy requirements and make the mathematics more realistic. And here's the exciting part. They're making progress. If you're enjoying this journey through the cosmos and want to see more content exploring the biggest questions in astrophysics, hit that subscribe button and give this video a thumbs up. Your support helps me continue creating these deep dives into the mysteries of our universe. Trust me, what's coming next will blow your mind. In 2012, physicist Harold White, who goes by the nickname Sonny, proposed a modification to the Alcubierre Drive. White was working at NASA's Johnson Space Center as part of something called the Advanced Propulsion Physics Laboratory, affectionately known as EagleWorks. His team wasn't just theorizing, they were actually conducting experiments related to space-time manipulation. White realized that by changing the shape of the warp bubble, making it more like a rounded donut rather than a sphere, you could drastically reduce the energy requirements. Instead of needing the mass of Jupiter, his calculations suggested you might only need the mass of something like Voyager 1, the spacecraft we launched back in 1977. That's roughly 722 kilograms. Suddenly, the idea didn't seem quite so impossible. Fast forward to 2020, and White's team made headlines again. They were studying something called Casimir cavities, tiny spaces between microscopic metal plates in a vacuum. In quantum mechanics, even empty space isn't truly empty. It's filled with virtual particles popping in and out of existence. When you place two metal plates extremely close together, you restrict which virtual particles can exist between them, creating a region of negative vacuum energy density. This is the Casimir effect, and it's been experimentally verified. While examining the energy patterns in these cavities, White noticed something extraordinary. The pattern matched exactly what you'd expect from the exotic matter needed for a warp drive. It was like finding a fingerprint at a crime scene that matches a suspect you thought was fictional. Now, does this mean we're about to build a warp drive tomorrow? Absolutely not. The Casimir effect produces negative energy on a scale so tiny it's almost meaningless for propulsion. We're talking about forces measured in nanonewtons between plates separated by distances smaller than a human hair's width. Scaling this up to move a spacecraft would require technology far beyond anything we currently possess. But the point is this: negative energy isn't just a mathematical abstraction anymore. It's something we can create and measure in a laboratory, even if only in minuscule amounts. This transforms warp drives from pure science fiction into something that might, just might, be science future. Let's talk about what's happened even more recently. In late 2025, a peer-reviewed study revisited warp drive physics with fresh eyes. Published in the journal Classical and Quantum Gravity, this research proposed a refined design that fits more naturally within general relativity. The study doesn't claim that faster-than-light travel is definitely possible, but it does show that warp space-time geometries may be more flexible than previously thought. The researchers explored different mathematical shapes for the warp bubble, investigating how space could be compressed and expanded in ways that minimize the exotic matter requirements. Another paper, published in December 2025, went even further. Scientists announced they'd developed what they call a fully physically realized model for a warp drive that might not require negative energy at all. If confirmed, this would be absolutely revolutionary because it would remove the single biggest obstacle to making warp drives a reality. But let's pump the brakes for a moment and inject some critical thinking here. These are theoretical models. They're solutions to Einstein's equations that work on paper, but that doesn't automatically mean nature will cooperate. Throughout the history of physics, we've found plenty of mathematical solutions that turned out to be physically impossible or unstable. Just because you can write down an equation doesn't mean you can build a machine. There are still enormous questions to answer. For instance, how would you actually generate and control a warp bubble? What would happen to the matter and energy around you as space contracts and expands? Would the bubble be stable, or would it collapse the moment you tried to activate it? And perhaps most troubling, would you be able to steer? Some calculations suggest that once you're inside a warp bubble, you'd be causally disconnected from the outside universe, unable to interact with anything, including your own ship's controls. There's also a fascinating problem called the horizon problem that physicist Stephen Hawking pointed out. When you create a warp bubble, the boundary between the warped space and normal space might have properties similar to a black hole's event horizon. This could lead to all sorts of bizarre and potentially dangerous effects. Particles and radiation could accumulate at the front of your bubble, and when you decelerate and the bubble collapses, all that energy might be released in a catastrophic burst. Imagine arriving at your destination and inadvertently obliterating it with a blast of high-energy particles. Not exactly the friendly first contact scenario we dream about. Another serious concern involves causality, which is just a fancy word for the cause and effect relationship that governs our universe. If you can travel faster than light, even by warping space, you might be able to create situations where effects precede their causes. This leads to paradoxes that make physicists very uncomfortable. Imagine sending a message to the past and preventing your own birth. These aren't just philosophical puzzles, they represent genuine problems with the consistency of physical law. Some researchers have proposed solutions, suggesting that the universe might have built-in mechanisms that prevent such paradoxes, but we honestly don't know. A recent study from 2025 explored something called causality regularized models that attempt to address these issues by introducing constraints on how warp bubbles can form and move. The mathematics is dense and complex, but the basic idea is that nature might enforce rules that keep time travel and paradoxes from occurring, even if warp drives become possible. Let's zoom out for a moment and consider what this all means in the grand scheme of cosmic exploration. Even if we solve every technical challenge, even if we discover how to generate exotic matter or find a workaround that doesn't require it, even if we build a stable, controllable warp drive, we're still facing limitations. The energy requirements, while potentially reduced from the original estimates, would still be enormous. We're talking about harnessing power sources that dwarf anything humanity currently possesses. Nuclear fusion, antimatter reactions, or perhaps something even more exotic, would be necessary. And here's something to ponder. Maybe the energy isn't the real bottleneck. Maybe it's our understanding of space-time itself. This actually connects to something I explored in another video on this channel called "Even if we could travel at light speed, it still wouldn't be enough." In that video, I break down why the distances between stars are so mind-bogglingly vast that even light-speed travel presents enormous challenges for exploration. The universe is expanding, time dilation affects how journeys are perceived, and the practical barriers to interstellar travel go way beyond just velocity. I highly recommend checking it out after this one. The link is in the description and on the card above. Now let's talk about something that often gets overlooked in discussions of faster-than-light travel, the engineering challenges. Assuming the physics works out, how would you actually build one of these things? You'd need materials that can withstand the stresses of warped space-time. You'd need power generation systems capable of producing and controlling astronomical amounts of energy with precision. You'd need navigation systems that can function in regions where the normal rules of space and time are bent. You'd need shielding to protect the crew from radiation and particles. And you'd need to test all of this, presumably starting with small-scale experiments and gradually working up to full-sized vessels. The Apollo program, which put humans on the moon, required the coordinated efforts of hundreds of thousands of people over more than a decade. A warp drive program would make Apollo look like a high school science project. But here's where I want to inject some wonder back into this conversation. Despite all these obstacles, despite these seemingly impossible requirements, the fact remains that we're having this discussion at all is extraordinary. 100 years ago, the idea of splitting the atom was theoretical speculation. 80 years ago, rockets barely reached the edge of space. 65 years ago, we hadn't sent a single human into orbit. 57 years ago, walking on the moon seemed like fantasy until we actually did it. The history of human technology is a story of achieving things that previous generations thought were impossible. We have a pretty good track record when we commit to ambitious goals. Consider the James Webb Space Telescope, which launched in December of 2021. This marvel of engineering sits at a gravitational balance point 1.5 million kilometers from Earth, observing the universe in infrared wavelengths with unprecedented clarity. The telescope's mirror is so precisely shaped that if you scaled it up to the size of the United States, the largest imperfection would be less than 2 inches tall. The instruments are cooled to mere degrees above absolute zero. The whole thing unfolds like an origami masterpiece after launch because it's too large to fit in any rocket while fully assembled. Humans built this. We figured out how to do something that seemed absurdly difficult, and now it's revealing galaxies that formed just a few 100 million years after the Big Bang. If we can do that, who's to say we can't eventually figure out warp drives? There's also an argument from convergent evolution in technology. Throughout history, when humans have encountered fundamental limits, we've found clever ways around them. We couldn't fly, so we invented aircraft. We couldn't survive in space, so we built spacecraft with life support. We couldn't see distant galaxies clearly through Earth's atmosphere, so we put telescopes in orbit. The pattern suggests that when confronted with the light-speed barrier, we won't just accept it. We'll search for loopholes, and we might just find them. The warp drive concept represents exactly this kind of creative problem-solving, accepting the constraint that matter can't exceed light speed, but finding a way to make space itself do the work. Let's discuss some alternative approaches that scientists are considering alongside warp drives. One idea involves wormholes, hypothetical tunnels, through space-time that could connect distant regions of the universe. If wormholes exist and could be made traversable, you might step through one end and emerge light-years away at the other end, effectively traveling faster than light without ever exceeding the local speed limit. The catch, once again, is exotic matter. Keeping a wormhole open and stable appears to require the same kind of negative energy that warp drives need. Another concept is the Krasnikov tube, proposed in 1995 by Russian physicist Sergei Krasnikov. This would involve modifying space-time along a path between 2 points so that the distance becomes shorter. It's similar to a warp drive, but operates more like building a highway through warped space rather than creating a bubble around a single ship. Then there's quantum entanglement, that spooky action at a distance that Einstein famously disliked. When two particles are entangled, measuring one instantly affects the other, regardless of the distance between them. This happens faster than light could travel between them. However, and this is crucial, you can't use entanglement to send information faster than light because the results appear random until you compare them through conventional slower-than-light communication. Still, some physicists wonder if there might be deeper principles at work that we don't yet understand, principles that could potentially be harnessed for faster-than-light communication or travel. This is highly speculative, but it reminds us that quantum mechanics continues to surprise us. What about simply going really, really fast without breaking the light speed limit? Projects like Breakthrough Starshot are exploring the possibility of using powerful lasers to push tiny spacecraft equipped with light sails to perhaps 20% of light speed. At that velocity, you could reach Proxima Centauri in about 20 years. That's not faster than light, but it's fast enough to make interstellar exploration feasible within a human lifetime. The technology required is challenging but doesn't require any exotic physics. Sometimes the best solution is the one that works with the laws we understand, rather than trying to bend them. Of course, a 20-year journey is still quite different from the instantaneous or near-instantaneous travel that warp drives promise. Here's something beautiful to consider. We are made of stardust, atoms forged in the hearts of ancient stars that exploded billions of years ago. Those atoms drifted through space, eventually coalescing into the solar system, the Earth, and ultimately, you. In a very real sense, you are the universe contemplating itself. The fact that we can even conceive of faster-than-light travel, that we can write equations describing how it might work, is a testament to the remarkable properties of consciousness and intelligence. We're not just passive observers of the cosmos, we're active participants, asking questions, seeking answers, and reaching for the stars that birthed us. The quest for faster-than-light travel represents more than just technological ambition. It speaks to something fundamental in human nature, our refusal to accept limits, our curiosity about what lies beyond the horizon, our desire to explore and understand. When our ancestors looked across the ocean and wondered what was on the other side, they built boats. When we looked up at the moon and wondered what it would be like to walk there, we built rockets. Now we look at the stars and wonder if we can reach them in our lifetimes. The pattern is clear. The question isn't really whether we'll try to build warp drives. The question is whether the universe will let us succeed. Let's dive deeper into the science behind why space itself can do things that matter cannot. This is where general relativity becomes both beautifully elegant and deeply strange. Einstein showed us that space and time aren't separate things. They're woven together into a four-dimensional fabric called space-time. Mass and energy curve this fabric, and that curvature is what we experience as gravity. When you drop a ball, it's not being pulled by some mysterious force. It's following the curved geometry of space-time created by Earth's mass. This insight completely revolutionized our understanding of the universe, and it opened doors to possibilities that Newton could never have imagined. Here's the key. Einstein's equations tell us how matter and energy curve space-time, but they don't place restrictions on how space-time itself can move or change. During the Big Bang, space expanded so rapidly that regions now separated by billions of light-years were once in contact. This inflationary period saw space expanding much faster than light could travel through it. This isn't theoretical speculation. We see evidence for it in the cosmic microwave background radiation, that faint afterglow of the Big Bang that fills the entire universe. The patterns in that radiation tell us that inflation happened, which means space can indeed expand at arbitrarily fast rates. If nature can do it, perhaps we can learn to do it too, at least on smaller scales. The universe is still expanding today, and that expansion is actually accelerating. We discovered this shocking fact in 1998 through observations of distant supernovae. Galaxies far away are receding from us faster and faster, driven by something we call dark energy. We don't really know what dark energy is. It makes up about 68% of the total energy content of the universe, yet it remains deeply mysterious. What we do know is that it causes space itself to expand. The most distant observable galaxies are moving away from us at speeds exceeding the speed of light, and they're doing this without violating relativity because they're not moving through space. Space is carrying them along. If the universe can do this naturally, unprompted, then manipulating space for our purposes might not be as far-fetched as it initially sounds. Now let's talk about some of the specific physics that goes into warp drive proposals. The Alcubierre metric, as it's called, is a solution to Einstein's field equations. These equations are incredibly complex, relating the curvature of space-time to the distribution of matter and energy. Finding solutions means discovering configurations of space-time that are mathematically consistent with the equations. The Alcubierre metric describes a bubble where space contracts in front and expands behind. Mathematically, this works. The question is whether you can create the matter and energy distribution required to generate that space-time geometry. That's where exotic matter comes in. Exotic matter with negative energy density would have bizarre properties. Unlike normal matter, which gravitationally attracts, exotic matter would gravitationally repel. It would exert negative pressure, pushing outward rather than pulling inward. In the Alcubierre Drive, this negative energy creates the expansion of space behind the ship. Think of it like this: positive energy and mass tell space to curve inward, creating gravity. Negative energy would tell space to curve outward, creating anti-gravity. The warp bubble requires a precise distribution of both types of energy to create the compression in front and expansion behind. Getting this balance right is crucial. Too much or too little in the wrong places, and the bubble either collapses or never forms in the first place. The Casimir effect that we mentioned earlier provides a tiny, tantalizing glimpse of negative energy. When you place two uncharged metal plates extremely close together in a vacuum, quantum fluctuations in the space around them create a measurable force pushing the plates together. This happens because the space between the plates has slightly less energy than the space outside, creating a relative negative energy density. In 1997, physicist Steve Lamoureux conducted a precise experiment confirming the Casimir effect, measuring forces that matched theoretical predictions. This was a landmark achievement, proving that quantum mechanics allows for regions of negative energy under specific conditions. However, and this is a big however, the Casimir effect is incredibly weak. The force between two plates separated by 1 micrometer is about the weight of a single bacterium. Scaling this up to produce the negative energy needed for a warp drive would require structures and techniques far beyond our current capabilities. Some researchers have proposed using advanced metamaterials, artificially engineered substances with properties not found in nature, to enhance the Casimir effect. Others have suggested that perhaps we don't need to create negative energy at all. Maybe there's a way to reshape the warp bubble geometry so that it only requires positive energy, or at least reduces the negative energy requirements to levels that might be achievable. This brings us to Harold White's modifications. In 2012, White proposed what's called a thick-wall warp bubble. Instead of a sharp boundary between warped and normal space, the transition would be gradual, spread over a larger volume. By running the numbers, White found that this change dramatically reduces the energy requirements. The original Alcubierre Drive needed something like -10 to the 64th kilograms of exotic matter. That's a 1 with 64 zeros after it, an incomprehensibly large number. White's modification brought it down to somewhere around 700 to 2,000 kilograms, depending on the specific parameters. That's still a lot of energy, but it's in the realm of things we can at least conceptualize building someday. White's team at NASA Eagle Works also experimented with something called the White-Jude warp field interferometer. This was an attempt to detect tiny distortions in space-time that might be created in the laboratory. The idea was to use a modified Michelson interferometer, a device that splits a laser beam and recombines it to detect incredibly small changes in path length. If they could generate even a microscopic warp field, the interferometer might pick it up. The results were intriguing but not conclusive. They detected some anomalies, but it's unclear whether these represented actual space-time distortions or just experimental noise. Still, the fact that serious scientists at a NASA facility were conducting these experiments shows how far warp drive research has come from pure science fiction. Let's address something important: the difference between going fast and warping space. If you accelerate a conventional spacecraft to high speeds, relativity comes into play. As you approach the speed of light, time dilation occurs. Time passes more slowly for you relative to observers at rest. If you traveled to a star 10 light-years away at 99% of light speed, the journey would take about 10 years as measured by someone on Earth, but due to time dilation, you'd experience only about 1.5 years passing. This is a real effect confirmed by countless experiments. Atomic clocks flown on airplanes tick at slightly different rates than identical clocks on the ground. GPS satellites must account for relativistic time dilation, or their navigation data would be useless. With a warp drive, however, you're not accelerating at all. You're sitting still inside your bubble while space moves around you. This means no time dilation. You could travel to a distant star and return without experiencing the asymmetric aging that conventional relativistic travel would cause. You and the people you left behind would age at the same rate. This is one of the most appealing features of warp drives. It solves not just the speed problem, but also the time problem. Interstellar journeys wouldn't require leaving your loved ones behind to age decades or centuries while you're gone. You could explore the galaxy and come home to the same world you left. But there's a flip side to this. Some physicists have pointed out that warp drives might create closed, time-like curves, paths through space-time that loop back on themselves. In simpler terms, you might be able to travel to the past. This sounds exciting until you realize it creates paradoxes that seem to violate the basic consistency of the universe. If you can travel to the past, you could prevent your own journey, creating a logical contradiction. Most physicists believe that something must prevent this, perhaps a principle we haven't discovered yet, that forbids closed, time-like curves. Stephen Hawking proposed a chronology protection conjecture, suggesting that the laws of physics conspire to prevent time travel. But we don't have a proof of this. It remains an open question. Recent work has explored what happens at the boundary of a warp bubble. Some calculations suggest that this boundary might accumulate matter and radiation as the bubble moves through space. Everything you encounter gets swept to the front of the bubble and piles up there. When you decelerate and the bubble collapses, all that accumulated energy gets released. For a journey across interstellar distances, the amount of energy could be devastating. Imagine arriving at your destination and unleashing a burst of high-energy particles equivalent to a supernova. This would obviously be catastrophic. Some researchers have proposed solutions, such as designing the bubble to allow particles to pass through or deflecting them somehow, but these add additional layers of complexity to an already incredibly complex concept. There's also the question of navigation and communication. Inside a warp bubble, you're in a region of severely distorted space-time. The light and other signals from the outside universe would be redshifted or blue-shifted dramatically, and you might not be able to see where you're going. You also couldn't send or receive radio signals because the bubble might be causally disconnected from the rest of the universe. This means you'd need to plot your course before engaging the warp drive and trust that nothing gets in your way during the journey. Given the vast emptiness of interstellar space, this might be acceptable, but it's certainly not ideal. You'd be flying blind, hoping your calculations were correct. Despite these challenges, research continues and new ideas emerge regularly. In 2021, physicist Eric Lentz published a paper proposing a new class of warp drive solutions that might not require negative energy at all. Lentz's approach uses configurations of positive energy arranged in specific ways to create the same compression and expansion of space that the Alcubierre Drive achieves with exotic matter. His solutions are called solitons, stable wave-like structures that maintain their shape as they propagate. The energy requirements are still enormous, equivalent to hundreds of times the mass of Jupiter, but the fact that they use only positive energy is significant. It means the fundamental physics might be less exotic than we thought. Lentz's work sparked considerable discussion in the physics community. Some researchers pointed out potential problems with his solutions, questioning whether they remain stable under certain conditions or whether they might violate other physical principles. Others built upon his ideas, exploring variations and refinements. This is how science progresses. Someone proposes an idea, others scrutinize it, find problems or improvements, and gradually we converge on a better understanding. The conversation around warp drives has become more sophisticated and nuanced over the past few years. We're moving beyond "is it possible" toward what specific challenges must we overcome. Another fascinating development involves the study of space-time itself at quantum scales. General relativity describes gravity as the curvature of space-time, but it's a classical theory. It doesn't incorporate quantum mechanics, the rules that govern the behavior of particles and fields at tiny scales. Physicists have been trying for decades to develop a quantum theory of gravity that unifies these two pillars of modern physics. Candidates include string theory, loop quantum gravity, and various other approaches. Understanding quantum gravity might reveal new possibilities for manipulating space-time that we can't currently imagine. Perhaps the exotic matter we need doesn't have to be created from scratch. Maybe it emerges naturally from quantum gravitational effects under the right conditions. Consider the quantum vacuum, that roiling sea of virtual particles constantly appearing and disappearing everywhere in space. The vacuum isn't empty. It's full of energy, sometimes called zero-point energy because it exists even at absolute zero temperature. Some calculations suggest that the energy density of the quantum vacuum is astronomically high, though we don't observe this in practice, which is its own mystery called the cosmological constant problem. If we could somehow tap into or manipulate vacuum energy, we might have access to the power source needed for warp drives. This is highly speculative, bordering on science fiction, but it illustrates how our incomplete understanding of fundamental physics leaves room for possibilities we haven't fully explored. Let's talk about what humanity would need to achieve before warp drives become practical. First, we'd need a much deeper understanding of quantum gravity and the quantum properties of space-time. This probably requires new experiments, perhaps involving extremely high energies or extremely precise measurements of gravitational effects. Second, we'd need to develop technologies for generating and controlling enormous amounts of energy. Fusion power would be a good start, but we might need something even more advanced, like antimatter reactors or exotic energy extraction from the vacuum. Third, we'd need materials, science breakthroughs to create structures that can withstand the stresses involved. Fourth, we'd need computational capabilities far beyond what we currently possess to model and control the complex dynamics of a warp bubble. None of these requirements is impossible in principle, but all of them represent major technological leaps. It's worth noting that throughout history, major leaps have often come from unexpected directions. The transistor, invented in 1947, revolutionized electronics in ways its inventors couldn't fully anticipate. The laser, developed in 1960, was initially called a solution looking for a problem. Yet now, lasers are everywhere, from surgery to telecommunications to grocery store scanners. Sometimes we develop a technology for one purpose and only later discover its transformative applications. Perhaps research in quantum computing or advanced materials or energy physics will yield insights that suddenly make warp drives seem more feasible. There's also the question of whether other civilizations in the universe have solved this problem. The cosmos is vast and ancient. Our galaxy alone contains hundreds of billions of stars, many with planets, and there are hundreds of billions of galaxies in the observable universe. Even if intelligent life is rare, the sheer number of opportunities suggests there might be other technological civilizations out there. If any of them are significantly older than us, they've had more time to develop advanced physics and engineering. Could some of them have warp drives? If so, where are they? This is the famous Fermi Paradox. If aliens exist, why haven't we seen evidence of them? One possible answer is that interstellar travel, even with warp drives, remains difficult and rare. Maybe the energy costs are so high that civilizations only undertake it occasionally for important reasons. Maybe warp drives turn out to be impossible after all, and the universe really does enforce the light speed limit strictly. Or maybe advanced civilizations exist but choose not to contact us, observing from afar, or simply not caring about a relatively young species like humanity. Another possibility, perhaps the most humbling, is that intelligent life is far rarer than we imagine, and we might be alone or nearly alone in our cosmic neighborhood. The silence we hear when we search for extraterrestrial signals could mean many things, and we don't yet know which interpretation is correct. Searching for extraterrestrial intelligence, or SETI, has been ongoing since 1960, when astronomer Frank Drake pointed a radio telescope at nearby stars and listened for signals. Decades later, we've expanded our search methods, looking for laser pulses, examining stars for megastructures that advanced civilizations might build, and analyzing exoplanet atmospheres for biosignatures. So far, we've found nothing definitive. Every mysterious signal, like the famous "wow" signal detected in 1977, has either faded away or been explained by natural phenomena. The universe seems quiet, but absence of evidence isn't evidence of absence. We've only searched a tiny fraction of the sky with limited sensitivity. The search continues, and every year our instruments get better. If we do detect evidence of an advanced civilization, one of the first questions we'll want to answer is whether they've mastered interstellar travel. If they have, studying their methods could revolutionize our own efforts. Of course, communicating with them would take time. Even at light speed, messages to nearby stars take years to arrive, and conversations would be painfully slow. Unless, of course, they've figured out faster-than-light communication as well. Some warp drive theories suggest that gravitational waves or other exotic signals might be able to propagate through warped regions of space faster than light travels through normal space. This is pure speculation, but it's fun to imagine. Let's bring this back to Earth and talk about what's happening right now in laboratories and universities around the world. Research into advanced propulsion isn't limited to warp drives. Scientists are exploring ion drives, nuclear propulsion, solar sails, and many other concepts that could make interplanetary and eventually interstellar travel more practical. Each advancement in propulsion technology teaches us something new about physics and engineering. The knowledge we gain from studying warp drives, even if they never become practical, could lead to breakthroughs in other areas. Understanding how to manipulate energy in space-time might have applications we haven't imagined yet. For example, research into the Casimir effect and vacuum energy could lead to new energy sources or better understanding of quantum field theory. Studies of exotic matter and negative energy might reveal new particles or forces. The mathematical techniques developed to analyze warp drive spacetimes could be useful in cosmology or black hole physics. Even if faster-than-light travel remains forever beyond our reach, the journey toward understanding it enriches our knowledge of the universe. Science is full of examples where the pursuit of one goal led to unexpected discoveries elsewhere. Alexander Fleming was studying bacteria when he accidentally discovered penicillin. The microwave oven was invented by accident while experimenting with radar. Who knows what we might stumble upon while chasing warp drives? There's something deeply human about this quest. We are explorers by nature. Our ancestors left Africa and spread across the entire planet, crossing oceans and mountains, adapting to every environment from Arctic tundra to tropical rainforests. We didn't do this because it was easy. We did it because curiosity and the drive to see what's over the horizon are woven into our DNA. Space is the ultimate frontier, the final ocean to cross. The fact that it's vastly more difficult than anything we've attempted before doesn't diminish our desire to try. If anything, it intensifies it. Consider the scale of what we're contemplating. The nearest star system, Alpha Centauri, is about 4.37 light-years away. That's roughly 41 trillion kilometers, or about 25 trillion miles. The fastest spacecraft we've ever built, the Parker Solar Probe, reaches speeds of about 192 kilometers per second during its closest approaches to the Sun. At that speed, it would still take over 6,700 years to reach Alpha Centauri. 6,700 years ago, humans were just beginning to develop agriculture and build the first cities. The idea of maintaining a mission for that length of time is absurd. We need something faster, much faster, and that's why concepts like warp drives capture our imagination so powerfully. The universe operates on scales that humble us. Our Milky Way galaxy spans about 100,000 light-years across. Even with a warp drive capable of going 10 times the speed of light, crossing the galaxy would take 10,000 years. You'd need to go hundreds or thousands of times faster than light to make galactic exploration practical within a human lifetime. And the Milky Way is just one galaxy among billions. The Andromeda Galaxy, our nearest large galactic neighbor, lies 2.5 million light-years away. To reach it in a reasonable time, you'd need speeds that make even the most optimistic warp drive proposals seem modest. The universe is teaching us a lesson in humility and ambition simultaneously. Yet here's what's remarkable. We can conceive of these journeys. We can write the mathematics, imagine the engineering, and dream of the day when humanity spreads beyond Earth to become a truly spacefaring civilization. The atoms in your body were forged in stellar furnaces billions of years ago. You are literally made of stardust, as astronomer Carl Sagan famously reminded us. The iron in your blood, the calcium in your bones, the carbon in your DNA, all of it was created in the cores of massive stars that lived, died, and exploded long before our solar system existed. In a very real sense, we are the universe becoming aware of itself, looking back at the cosmos that created us and asking how we might explore it. This perspective shifts the question of faster-than-light travel from a purely technical problem to something more profound. It's about humanity's place in the cosmic story. Are we confined forever to one small planet orbiting an ordinary star? in the suburbs of an average galaxy? Or will we find ways to spread outward, to touch other worlds, to perhaps encounter other forms of life and consciousness? The answer to that question depends partly on physics, what the universe allows, but also on human determination and ingenuity. History suggests we shouldn't underestimate what's possible when people commit to achieving something extraordinary. Let's examine some specific numbers to appreciate the energy scales involved. The speed of light is approximately 299,792,458 meters per second. The kinetic energy of an object increases with the square of its velocity in classical physics, but as you approach light speed, relativistic effects take over and the energy required approaches infinity. This is why nothing with mass can reach light speed through conventional acceleration. You'd need infinite energy, which is obviously impossible, but with a warp drive you're not accelerating the ship itself. You're manipulating the space around it, which requires a different kind of energy budget. Early calculations suggested you'd need energy equivalent to the mass of Jupiter converted entirely to energy via Einstein's famous equation E equals mc squared. Jupiter's mass is about 1.9 times 10 to the 27th kilograms. Converting that to energy gives you roughly 1.7 times 10 to the 44 joules. That's 17 followed by 43 zeros. For comparison, the total energy output of the Sun over its entire 10 billion year lifetime is around 10 to the 44 joules. You'd need to capture and convert the entire energy output of a star to power a single warp drive journey. Clearly, this isn't practical. Harold White's modifications brought the requirements down dramatically to perhaps the mass-energy equivalent of a large spacecraft, somewhere around 700 to 2,000 kilograms. Using E equals mc squared again, that's roughly 6 times 10 to the 19 joules. That's still an enormous amount of energy, equivalent to about 15 million tons of TNT, or roughly 1,000 times the energy released by the atomic bomb dropped on Hiroshima. But it's at least conceivable. If we develop efficient antimatter-matter annihilation reactors, or discover how to tap vacuum energy, or find some other exotic power source, we might be able to generate this much energy. It's no longer in the realm of star-level power required, but rather incredibly advanced, but maybe achievable technology required. More recent proposals, like Eric Lentz's positive energy warp drive, push the requirements back up again to hundreds of Jupiter masses. This seems like a step backward, except for one crucial detail. It doesn't require exotic matter. The distinction is important. Exotic matter might not exist at all, or might be impossible to produce in the quantities needed. Positive energy, on the other hand, definitely exists. We just need absurdly large amounts of it. Perhaps future discoveries will reveal ways to reduce these requirements, just as White's modifications reduced the original Alcubierre requirements. The field is young and we're still exploring the parameter space of possible solutions. There's another consideration that often gets overlooked: political and social will. Building something as ambitious as a warp drive would require coordination on a global scale, resources far beyond what any single nation could muster, and sustained commitment over decades or even centuries. The International Space Station, one of humanity's most impressive collaborative achievements, cost roughly $150 billion and required the cooperation of 15 countries over more than 20 years. A warp drive program would make the ISS look like a small investment. We're talking about potentially the largest project humanity has ever undertaken, rivaling or exceeding the cost and complexity of all our space programs combined. Would humanity come together for such an endeavor? History gives us mixed signals. We've accomplished extraordinary things when motivated by competition, like the space race during the Cold War, or by existential threats, like the Manhattan Project during World War II. But we've also failed to cooperate on problems that clearly require global action, like climate change. Building a warp drive wouldn't have the urgency of a wartime crisis or the competitive drive of a race between superpowers. It would need to be motivated by exploration, discovery, and the long-term survival and flourishing of our species. Whether we possess the collective wisdom and vision to commit to such a project remains an open question. Let's consider the timeline. When might warp drives become possible, assuming they're physically feasible? Predictions are notoriously difficult, but we can make some educated guesses. First, we need major breakthroughs in theoretical physics, particularly a working theory of quantum gravity. Many physicists hope to achieve this within the next 50 to 100 years, though it could take longer. Second, we need energy technologies far beyond our current capabilities. Fusion power, which we've been trying to achieve for decades, might become practical in the next 20 to 50 years. More exotic energy sources would require additional time. Third, we need the engineering and materials science to build the actual device. Adding all this up, optimistic estimates suggest the late 22nd century at the earliest, more likely the 23rd or 24th century. That's 200 to 300 years from now. It sounds like a long time, but consider that 300 years ago in 1726, Isaac Newton had only recently died and the Industrial Revolution hadn't yet begun. Electricity was a curiosity, not a technology. The idea of computers, airplanes, or space travel would have seemed like pure fantasy. If you'd told someone in 1726 what the world would look like in 2026, they wouldn't have believed you. Extrapolating forward another 300 years is equally difficult. Technologies we can barely imagine might be commonplace. Warp drives might be just one achievement among many that transform civilization beyond recognition. Of course, there's no guarantee we'll survive that long as a technological civilization. We face challenges that could derail or destroy our progress: climate change, nuclear war, pandemics, artificial intelligence risks, and others we might not foresee. The next few centuries are crucial. If we navigate them successfully, solving the problems we've created and maturing as a species, then projects like warp drives become realistic possibilities. If we don't, well, it won't matter whether faster-than-light travel is possible because we won't be around to attempt it. This adds urgency to our current choices. The decisions we make today about how we treat our planet, how we develop powerful technologies, and how we cooperate with one another will determine whether future generations get the chance to reach for the stars. Let's pivot to discuss some of the most exciting recent experiments and observations. In February of 2026, researchers reported progress in understanding vacuum energy using advanced Casimir cavity experiments. By manipulating the geometry of the cavities and using quantum-engineered materials, they were able to enhance the Casimir effect by several orders of magnitude compared to simple parallel plates. While still nowhere near the levels needed for propulsion, these experiments prove that we're learning to manipulate quantum vacuum effects with increasing precision. Each improvement brings us slightly closer to understanding whether exotic energy manipulation might be possible on useful scales. Another intriguing development involves gravitational wave astronomy. The LIGO and Virgo detectors have been observing gravitational waves from colliding black holes and neutron stars since 2015. These observations are teaching us about space-time dynamics in extreme conditions. When massive objects merge, they create ripples in space-time that propagate outward at the speed of light. By studying these ripples, we learn how space-time responds to violent disturbances. This knowledge could potentially inform warp drive design, helping us understand how to create and control space-time distortions. It's a bit like studying ocean waves to learn how to build better ships. The more we understand about how space-time behaves naturally, the better equipped we'll be to manipulate it artificially. The James Webb Space Telescope and other advanced observatories are revealing the universe in unprecedented detail. We're discovering exoplanets, planets orbiting other stars, at a remarkable rate. As of 2026, we've confirmed over 5,000 exoplanets, with thousands more candidates awaiting verification. Many of these planets orbit in the habitable zones of their stars, where liquid water could exist on their surfaces. Each discovery makes the universe seem a little less empty and increases the potential destinations for future exploration. What's the point of developing warp drives if there's nowhere interesting to go? The growing catalogue of exoplanets provides compelling targets, worlds we might want to visit, study, or even colonize someday. Some of these exoplanets are tantalizingly close. Proxima Centauri b, discovered in 2016, orbits our nearest stellar neighbor at a distance where temperatures might allow liquid water. It's only 4.24 light-years away, practically in our backyard by cosmic standards. TRAPPIST-1, a system discovered in 2017, contains 7 Earth-sized planets orbiting a small, cool star about 39 light-years away. At least 3 of these planets are in the habitable zone. These worlds represent the kind of destinations that make interstellar travel feel urgent and necessary. We've found the places we want to explore. Now, we need the means to get there. But let's be realistic about what we'd find. Even if we reach these exoplanets, the likelihood of finding complex life, let alone intelligent civilizations, is probably low. Life might be common in the universe, or it might be extraordinarily rare. We simply don't know because we have a sample size of 1, Earth. Every living thing we've ever discovered, from bacteria to blue whales, shares the same basic biochemistry and ancestry. We're all part of one family tree of life that arose here on Earth about 3.8 billion years ago. Until we find a second, independent example of life, we can't say how common or rare it is. The discovery of even simple microbial life on Mars or Europa or Enceladus would be revolutionary, telling us that life emerges readily when conditions are right. The search for biosignatures in exoplanet atmospheres is one of the most exciting frontiers in astronomy right now. When starlight passes through a planet's atmosphere on its way to us, molecules in that atmosphere absorb specific wavelengths, leaving dark lines in the spectrum. By analyzing these lines, we can identify what gases are present. Oxygen, for example, is highly reactive and shouldn't persist in an atmosphere unless something continually replenishes it. On Earth, that something is photosynthetic life. If we detect oxygen along with other biosignature gases like methane in an exoplanet's atmosphere, it might indicate life. The James Webb Space Telescope is beginning to analyze exoplanet atmospheres with the sensitivity needed to detect these subtle signals. Imagine we do detect signs of life on a planet 40 light-years away. What then? At our current fastest speeds, it would take hundreds of thousands of years to get there. Even with optimistic near-future propulsion like light sails pushed by lasers, we're talking about 800 to 1,000 years for a journey. That's a multi-generational starship, a concept that presents enormous challenges. How do you maintain a society and technology base aboard a spacecraft for 40 generations? How do you ensure the mission's goals remain relevant to people born into the journey who will die before reaching the destination? These problems are solvable in principle, but they're daunting. A warp drive, if achievable, eliminates these issues entirely. You could make the trip in weeks, months, or at most a few years. The crew who departs would be the crew who arrives. Let's discuss some of the philosophical implications of faster-than-light travel. If it becomes possible, it would fundamentally change humanity's relationship with the universe. We'd transition from being permanently confined to our corner of space to having access to the galaxy and potentially beyond. This would be one of the most significant transitions in human history, comparable to the emergence of multicellular life, the development of intelligence, or the invention of agriculture. It would open possibilities we can barely imagine, studying alien ecosystems, witnessing phenomena like nearby supernovae or black holes up close, establishing colonies on distant worlds, and perhaps encountering other civilizations. But it would also raise profound questions about responsibility and ethics. If we can reach other star systems, should we? What if we find planets with primitive life? Would we have the right to colonize them, potentially disrupting or destroying native ecosystems? What if we encounter intelligent species? How should we interact with them? Science fiction has explored these questions for decades, but they might become real policy decisions within a few centuries. Humanity's track record with first contact scenarios on Earth has been mixed at best. When technologically advanced civilizations encountered less advanced ones, the results were often catastrophic for the less advanced group. We'd need to develop ethical frameworks for interstellar exploration long before we actually achieve it. There's also the question of what happens to human civilization if the stars become accessible. Would Earth remain important, or would it become just one world among many? Would humanity fragment into separate populations on different planets, potentially evolving in different directions over thousands of years? Or would faster-than-light travel keep us connected, allowing trade, communication, and cultural exchange across light years? These scenarios lead to vastly different futures. In one, we remain essentially human and unified. In another, our descendants might become so diverse that they're barely recognizable as the same species. Both possibilities are fascinating and a little unsettling. Let's return to the physics and discuss some alternatives to the Alcubierre Drive that researchers are exploring. One concept is the Natário Drive, proposed in 2001 by Portuguese mathematician José Natário. Like the Alcubierre Drive, it creates a warp bubble, but the mathematics is structured differently. The Natário Drive might require less exotic matter and could be more stable, though it still faces many of the same fundamental challenges. Another idea is the Bobrick-Martyr Drive, proposed in 2021. This approach focuses on creating physically realizable warp drives by imposing constraints that ensure the solutions respect all known physical laws. The trade-off is reduced performance. You might not achieve arbitrarily fast speeds, but the drive might actually be buildable with advanced technology. Then there's the concept of using black holes as natural warp drive engines. Black holes warp space-time dramatically, and some physicists have speculated about whether we could harness this warping for propulsion. A rotating black hole, called a Kerr black hole, has particularly interesting properties. It drags space-time around with it in a phenomenon called frame dragging. If you could position a spacecraft in just the right orbit around a Kerr black hole, you might be able to extract energy from its rotation and use it for propulsion. This is called the Penrose process, proposed in 1969. Whether this could actually achieve faster-than-light travel is doubtful, but it illustrates how extreme gravitational environments might offer propulsion opportunities we don't fully understand yet. Wormholes remain another tantalizing possibility. The equations of general relativity allow for solutions where space-time folds back on itself, creating shortcuts between distant regions. If you could create and stabilize a wormhole, you could step through one end and emerge light years away at the other end almost instantly. The problems are formidable. First, naturally occurring wormholes, if they exist at all, would probably be microscopic and incredibly short-lived, existing only at the quantum scale for tiny fractions of a second. Second, keeping a wormhole open appears to require exotic matter with negative energy, the same problem that plagues warp drives. Third, even if you could create and stabilize a wormhole, you'd need to position its ends where you want them, which might require conventional slower-than-light travel to set up in the first place. Physicist Kip Thorne, who won the Nobel Prize for his work on gravitational waves, studied traversable wormholes in the 1980s. His work was partly inspired by Carl Sagan, who was writing the novel Contact and wanted a scientifically plausible mechanism for his characters to travel across the galaxy. Thorne worked out the conditions necessary for a wormhole to remain open and allow safe passage. The conclusion was that you'd need exotic matter, but the amount might be less than what a warp drive requires. Some estimates suggest that exotic matter with negative energy equivalent to only a few solar masses might suffice, distributed in a specific configuration around the wormhole's throat. That's still an absurd amount, but it's at least conceivable that a sufficiently advanced civilization might manage it. Here's something mind-bending. If you could create a wormhole and move one end of it at high speed relative to the other end, relativistic time dilation would cause the two ends to experience time at different rates. This could turn the wormhole into a time machine, allowing travel between different points in time as well as space. Again, this raises causality problems and paradoxes. Most physicists believe something prevents this, perhaps quantum effects that destabilize the wormhole if you try to use it for time travel. But we don't have a complete understanding, so the possibility remains open. The universe might have rules we haven't discovered yet that elegantly resolve these issues. Let's talk about the practical steps researchers are taking right now to advance our understanding. Several universities and research institutions have programs studying advanced propulsion concepts. The Tau Zero Foundation, founded in 2006, brings together scientists and engineers interested in interstellar flight. They hold conferences, publish research, and promote education about the challenges and possibilities of reaching other stars. NASA's Innovative Advanced Concepts program funds early-stage research into revolutionary aerospace ideas, including advanced propulsion. While warp drives are considered highly speculative, related research on space-time physics and exotic propulsion receives attention. The private sector is also getting involved. Organizations like the Limitless Space Institute, where Harold White works, are funded by private donations and aim to advance the science and technology needed for interstellar travel. Billionaires and tech entrepreneurs who made fortunes in other industries are increasingly interested in space exploration. While most of their efforts focus on more near-term goals like Mars colonization or satellite networks, the long-term vision often includes interstellar travel. Money alone won't solve the physics problems, but it can fund research, attract talented scientists, and keep the field moving forward during periods when governments might not prioritize such long-term projects. Educational initiatives matter too. Inspiring the next generation of physicists, engineers, and explorers is crucial. When young people learn about concepts like warp drives, even though they're speculative, it encourages them to study science and push the boundaries of what's possible. Many of today's leading researchers became interested in physics because of science fiction that made them wonder whether faster-than-light travel could be real. That sense of wonder, that curiosity about the universe and our place in it, drives progress in ways that are hard to quantify but absolutely essential. We should also acknowledge the role of science fiction in shaping our thinking about interstellar travel. Shows like Star Trek, movies like Interstellar, and countless books have kept these ideas alive in popular imagination for generations. While science fiction often takes liberties with physics for storytelling purposes, the best of it engages seriously with real science and inspires audiences to think about the possibilities. Interstellar, released in 2014, featured physicist Kip Thorne as a scientific consultant, ensuring that its depictions of black holes and relativistic effects were as accurate as possible within the constraints of dramatic storytelling. The movie sparked widespread public interest in concepts like time dilation and gravitational physics. Star Trek's warp drive, introduced in the original series in 1966, has become so iconic that it directly inspired Miguel Alcubierre to work out the mathematics of how such a device might actually function. He titled his paper, "The Warp Drive, Hyperfast Travel Within General Relativity," as an explicit reference to the show. This kind of feedback loop between fiction and science is powerful. Fiction imagines possibilities, scientists investigate whether they're real, and their findings inspire new fiction. The cycle continues, each iteration adding more sophistication and detail to our collective vision of the future. Let's dive deeper into some of the mathematics involved, though we'll keep it conceptual rather than drowning in equations. General relativity is expressed through Einstein's field equations, which can be written compactly but contain enormous complexity. On one side of the equation, you have quantities describing the curvature of space-time. On the other side, you have quantities describing the distribution of matter and energy. The equation says these two sides must be equal, meaning matter and energy. Tell space-time how to curve, and curved space-time tells matter and energy how to move. Finding solutions to these equations means discovering configurations where both sides balance. The Alcubierre metric is one such solution. It describes a particular geometry of space-time where a bubble region maintains flat space inside while warping the space around it. Mathematically, this is represented by something called the metric tensor, a mathematical object that encodes all the information about distances and time intervals in curved space-time. The Alcubierre metric has specific mathematical properties that allow the bubble to move through space at any speed. When physicists plug this metric back into Einstein's equations to see what kind of matter and energy distribution would be required to create it, they find that you need negative energy density in certain regions. That's where exotic matter enters the picture. The beauty of mathematics is that it allows us to explore possibilities that we can't yet test experimentally. We can write down equations for configurations that might not exist in nature and see what they imply. Sometimes these explorations lead nowhere, but other times they reveal deep insights. Black holes were mathematical curiosities for decades before we found convincing evidence they actually exist in the universe. In 1916, Carl Schwarzschild found a solution to Einstein's equations describing the space-time around a perfectly spherical mass. The solution had a singularity, a point where the mathematics broke down, and a boundary called the event horizon beyond which nothing could escape. For years, many physicists thought these were just mathematical artifacts, not real objects. Today, we know black holes are common, with millions or billions scattered throughout every galaxy. Could warp drives follow a similar trajectory? It's possible. We have the mathematics describing how they'd work. We have ideas, however speculative, about how the necessary conditions might be created. What we lack is the technology and perhaps some crucial piece of physics that would make it all come together. But the fact that the mathematics works within general relativity is significant. It means we're not asking the universe for something that violates its fundamental rules. We're asking if there's a way to satisfy those rules in a configuration that happens to allow faster-than-light travel. The universe might say no for reasons we haven't discovered yet, but it hasn't definitively said no based on what we currently know. Let's consider the role of computational simulations in advancing this field. Modern supercomputers allow us to model complex physical systems with incredible detail. Researchers can simulate the formation and evolution of warp bubbles, testing different configurations to see which ones are most stable or efficient. These simulations reveal problems that aren't obvious from the equations alone. For example, some warp drive configurations that look fine mathematically turn out to be unstable when you simulate them, collapsing or developing singularities. Other configurations might create dangerous levels of radiation or particle acceleration. By simulating these scenarios, we can rule out designs that won't work and refine those that show promise. Advances in quantum computing might eventually help with these simulations. Quantum computers excel at certain types of calculations that are difficult for classical computers, particularly those involving quantum systems. Since the exotic matter or vacuum energy manipulation we'd need for warp drives involves quantum effects, quantum computers might be able to model these scenarios more accurately and efficiently than conventional supercomputers. This is speculative, but it illustrates how progress in one field of technology can enable progress in seemingly unrelated fields. The path to warp drives might wind through unexpected territory. There's also fascinating work being done on metamaterials, artificially engineered substances with properties not found in natural materials. By arranging structures on microscopic scales, scientists can create materials that interact with light or other electromagnetic radiation in unusual ways. Metamaterials can bend light in directions that natural materials cannot, or create negative refractive indices. Some researchers have speculated that similar principles might apply to gravity and space-time. Could we create gravitational metamaterials that interact with space-time in exotic ways? It's a long shot, but metamaterials have already achieved things that were thought impossible, so perhaps there's potential here. Let's discuss the concept of energy density in more detail, because it's central to understanding warp drives. Energy density is simply the amount of energy contained in a given volume of space. Normal matter has positive energy density. The more matter you pack into a space, the higher the energy density. Exotic matter with negative energy density is the opposite. It represents a deficit of energy compared to empty vacuum. The Casimir effect creates tiny regions of negative energy density, but they're incredibly weak. To put this in perspective, the negative energy density between Casimir plates separated by 1 micrometer is about negative 0.001 joules per cubic meter. A warp drive might need negative energy densities of perhaps 10 to the 30 joules per cubic meter or higher, depending on the design. That's a difference of more than 30 orders of magnitude. Can we possibly achieve such enormous negative energy densities? Nobody knows for sure. One idea involves using extremely intense electromagnetic fields to enhance quantum vacuum effects. When you apply a very strong electric or magnetic field, you can polarize the vacuum, affecting how virtual particles behave. This might amplify the Casimir effect or create other sources of negative energy. The problem is that the field strengths required are absurdly high, approaching or exceeding what we can currently generate even in the most advanced particle accelerators. We're talking about fields so intense that they'd be found near the surfaces of neutron stars or in the collision zones of ultra-powerful laser pulses. Speaking of lasers, there's interesting research into using extremely high-intensity laser pulses to study vacuum physics. Facilities like the National Ignition Facility in the United States or the European XFEL in Germany can create laser pulses with intensities measured in watts per square centimeter that reach into the 10 to the 22 range or higher. At these intensities, you start to see quantum electrodynamic effects where photons, particles of light, interact with the quantum vacuum in measurable ways. Pushing these intensities even higher might allow us to probe vacuum structure in unprecedented detail, potentially revealing whether negative energy manipulation on useful scales is possible. Another avenue of research involves accelerators and high-energy physics. The Large Hadron Collider near Geneva, Switzerland, the most powerful particle accelerator ever built, smashes protons together at energies approaching 7 trillion electron volts per proton. These collisions recreate conditions similar to those that existed a tiny fraction of a second after the Big Bang. By studying what happens at these extreme energies, physicists learn about fundamental particles and forces. Some theories of physics beyond the standard model predict new particles or forces that might emerge at high energies. Could any of these be relevant to warp drives? It's impossible to say without discovering them first, but history shows that exploring extreme conditions often reveals surprises. The connection between energy and mass, expressed in Einstein's equation E equals mc squared, is worth reflecting on. This equation tells us that mass and energy are interchangeable, two forms of the same thing. A small amount of mass contains a tremendous amount of energy. 1 kilogram of matter converted entirely to energy releases about 9 times 10 to the 16th joules, equivalent to roughly 21 megatons of TNT. This is why nuclear reactions, which convert tiny fractions of mass to energy, are so powerful. Complete matter-antimatter annihilation converts all the mass to energy, making it the most efficient energy source theoretically possible within known physics. If we could harness antimatter efficiently, it might provide the energy needed for advanced propulsion, possibly including warp drives. The problem is that antimatter is incredibly difficult to produce and store. When antimatter contacts normal matter, both annihilate instantly, releasing energy. This means you can't store antimatter in conventional containers. It has to be held using electromagnetic fields in perfect vacuum, and even then, tiny losses occur. Current technology can store only minuscule amounts of antimatter for short periods. Scaling up to industrially useful quantities would require breakthroughs in production and containment technology. But if we achieved this, the energy density of antimatter fuel would be unmatched, potentially enabling propulsion systems far beyond anything we have today. There's also the question of where antimatter might be found naturally in the universe. Some astrophysical processes, like matter falling into black holes or certain types of supernovae, produce antimatter. Could a sufficiently advanced civilization harvest antimatter from these sources rather than manufacturing it? This sounds like science fiction, but it's based on real physics. The challenges would be immense, approaching a black hole or supernova remnant, capturing the antimatter, storing it safely, and transporting it back. But these are engineering problems, not fundamental physics problems. Given enough time and technological development, they might be solvable. Let's shift perspective and think about the broader context of human spaceflight. We've been launching humans into space for only about 65 years, since Yuri Gagarin's historic flight in 1961. In that relatively short time, we've gone from brief suborbital hops to sustained presence aboard the International Space Station, which has been continuously occupied since November of 2000. We've walked on the Moon, sent probes to every planet in our solar system, and landed rovers on Mars. The pace of progress has been extraordinary, even if it sometimes feels slower than we'd like. Looking forward, the next few decades will likely see humanity return to the Moon, with plans for permanent lunar bases. NASA's Artemis program aims to land astronauts on the Moon again in the late 2020s, this time establishing sustained presence rather than brief visits. Private companies like SpaceX, Blue Origin, and others are developing heavy-lift rockets and spacecraft that could make Mars missions possible in the 2030s or 2040s. China, India, and other nations are expanding their space programs. We're entering a new era of space exploration characterized by international cooperation alongside private enterprise, with goals extending beyond Earth orbit to the surfaces of other worlds. These near-term goals are stepping stones. Every advancement in propulsion, life support, radiation shielding, and other technologies needed for Moon and Mars missions brings us incrementally closer to the capabilities needed for interstellar travel. We learn by doing. The challenges of sustaining humans in space for months or years teach us lessons applicable to the decades-long or generation-spanning journeys that interstellar travel would require, even with advanced propulsion. And the economic and political frameworks we develop for space exploration will shape whether humanity can commit to projects as ambitious as building warp drives. Space exploration also provides perspective on our place in the universe. The famous pale blue dot photograph taken by Voyager 1 in 1990 from about 6 billion kilometers away shows Earth as a tiny speck barely visible against the vastness of space. Carl Sagan's reflection on this image is worth remembering. He noted that every human who ever lived, every joy and suffering, every civilization and conflict happened on that tiny mote of dust suspended in a sunbeam. This perspective is simultaneously humbling and inspiring. It reminds us how small we are, but also how precious life and consciousness are in this vast, seemingly empty universe. If we develop faster-than-light travel, we'll take that perspective with us to the stars. We'll carry the knowledge that life is rare and valuable, that our actions have consequences, and that exploration requires not just technological capability, but wisdom and ethics. The universe won't care whether we're ready for the responsibility that comes with such power. It'll be up to us to ensure we use it wisely. This is one reason why discussions about warp drives aren't just about physics and engineering. They're about who we are as a species and who we want to become. Let's return to some of the cutting-edge theoretical work being done. One fascinating area is the study of closed time-like curves, those paths through space-time that loop back on themselves, potentially allowing time travel. Some warp drive configurations, if you manipulate them in certain ways, might create these curves. Physicist Frank Tipler showed in the 1970s that a rotating cylinder of infinitely dense matter could create closed time-like curves. Of course, Infinitely dense matter doesn't exist, so this is purely theoretical. But similar principles might apply to other configurations involving rapidly rotating or moving regions of warped space-time. The problem with closed, time-like curves is that they lead to paradoxes. The classic example is the grandfather paradox. If you travel back in time and prevent your grandfather from meeting your grandmother, you'd never be born, so you couldn't travel back to prevent their meeting, which means you would be born, and so on. The logical contradiction seems to suggest that nature must prevent such scenarios. Stephen Hawking's chronology protection conjecture proposes that quantum effects would destroy any attempt to create a time machine, causing it to fail right at the moment it might succeed. However, this remains a conjecture, not a proven theorem. Some physicists have explored whether the universe might allow closed time-like curves, but enforce consistency by constraining what can happen when you travel along them. The Novikov self-consistency principle proposed in the 1980s suggests that if time travel is possible, events must always be self-consistent. You can travel to the past, but you can't change it in ways that would create paradoxes. You'd find that your actions always were part of history, creating a self-consistent timeline. This is philosophically interesting, but raises questions about free will and determinism that are beyond the scope of physics to answer definitively. For warp drives, the message is clear: we need to be very careful about the space-time geometries we create. Some configurations might be physically possible, but lead to causality problems. Others might be both possible and causality safe. Research published in 2025 on causality regularized warp drive models attempts to identify constraints that would prevent time travel while still allowing faster-than-light motion. The mathematics is complex, involving careful analysis of light cones, which describe the paths that light and causally connected events must follow through space-time. If these constraints can be satisfied, it would remove one of the major theoretical objections to warp drives. Another active area of research involves numerical relativity, using computers to solve Einstein's equations for complex scenarios. Simulating a warp drive requires tracking how space-time evolves as the bubble forms, moves, and potentially collapses. These simulations are computationally intensive because you need to model space-time in 3 dimensions plus time, with sufficient resolution to capture the details of the warped regions. Recent advances in numerical methods and computing power have made such simulations more feasible. Researchers can now run simulations that were impossible just a decade ago, revealing behaviors and instabilities that weren't apparent from analytical calculations alone. One result from these simulations is that many simple warp drive configurations are unstable. They either collapse rapidly or develop singularities where the curvature of space-time becomes infinite. This doesn't necessarily mean warp drives are impossible, but it does mean we need more sophisticated designs. The search is on for configurations that are both physically realizable and stable over the duration of a journey. This requires balancing many competing factors: energy requirements, stability, controllability, and avoiding dangerous side effects like excessive radiation or causality violations. There's also research into what happens at the quantum level in regions of extreme space-time curvature. Quantum field theory in curved space-time is the framework for studying how quantum fields behave when space-time isn't flat. This field has given us important results like Hawking radiation, the prediction that black holes emit thermal radiation and slowly evaporate over time. Similar quantum effects might be important for warp drives. For example, the intense curvature at the boundary of a warp bubble might cause quantum fields to behave in unexpected ways, potentially creating particle-antiparticle pairs or producing radiation. Understanding these effects is crucial for assessing whether warp drives could be safe for occupants and surroundings. Let's discuss the international dimension of this research. Science is fundamentally collaborative and international. The most important discoveries often come from researchers in different countries, sharing ideas and building on each other's work. General relativity was developed by Einstein in Germany and Switzerland, but physicists worldwide contributed to its refinement and application. Today, research on advanced propulsion and exotic physics happens in universities and institutes across the globe. The United States, Europe, China, Japan, Russia, India, and elsewhere. International conferences bring researchers together to share findings and debate ideas. This global cooperation is essential for tackling challenges as immense as faster-than-light travel. No single nation has the resources or expertise to solve all the problems alone. We need theoretical physicists developing the mathematics, experimental physicists testing predictions in laboratories, astronomers observing relevant phenomena in space, engineers designing possible implementations, and computer scientists running simulations. This requires coordinated efforts across multiple disciplines and nations. Organizations like the International Astronautical Federation and various professional societies facilitate this cooperation, ensuring that knowledge flows freely across borders. There's also the question of whether governments and institutions will support this research over the long term. Funding for basic science is always competitive, with many worthy projects vying for limited resources. Research on warp drives and exotic propulsion is highly speculative, unlikely to yield practical applications for many decades, if ever. In the current funding climate, convincing agencies to invest substantially in such long-term, uncertain projects is difficult. Most funding goes to more near-term goals with clearer payoffs. This is understandable but potentially short-sighted. History shows that fundamental research often produces unexpected breakthroughs that transform society in ways nobody anticipated. The transistor emerged from Bell Labs research into quantum mechanics and solid-state physics. Nobody working on that research in the 1940s envisioned smartphones, laptops, or the internet. Yet all of these depend on transistors. GPS depends on understanding general relativity to account for time dilation effects on satellite clocks. If we'd never funded relativity research because it seemed too abstract and impractical, we wouldn't have GPS today. The same principle applies to research on warp drives and exotic physics. Even if warp drives never materialize, the knowledge gained along the way will likely have applications we can't currently foresee. We should also consider the role of serendipity in scientific discovery. Many of the most important breakthroughs came from unexpected directions. Penicillin was discovered by accident when Alexander Fleming noticed that a contaminating mold killed bacteria in his petri dishes. The cosmic microwave background radiation, evidence for the Big Bang, was discovered in 1964 by Arno Penzias and Robert Wilson, who were trying to eliminate annoying noise from a radio antenna. X-rays were discovered by Wilhelm Röntgen in 1895 while experimenting with cathode ray tubes. He wasn't looking for a new form of radiation, but when he noticed that a screen across the room glowed when he activated the tube, he investigated and discovered something revolutionary. The path to warp drives might follow a similar pattern. Perhaps someone working on quantum computing or metamaterials or plasma physics will stumble upon an effect that turns out to be relevant to space-time manipulation. Perhaps observations from a gravitational wave detector or space telescope will reveal natural phenomena that provide clues about exotic matter. Perhaps a student working on a theoretical problem will discover a mathematical relationship that opens new possibilities. We can't predict where breakthroughs will come from, which is why supporting a broad base of fundamental research is so important. The more scientists working on diverse problems, the higher the probability that someone will find something unexpected and important. Let's imagine, just for a moment, what it would be like to actually travel in a warp drive. Assuming all the physics and engineering problems are solved, you board a spacecraft equipped with warp drive technology. The journey you're about to undertake would take thousands of years at conventional speeds, but with the warp drive, you'll arrive in perhaps a few weeks or months. As the drive activates, you don't feel acceleration. You're not moving in the conventional sense. Instead, space itself begins to shift around your ship. Out the viewports, if the optics work properly through the distorted space-time, you might see stars shifting in unusual ways as space contracts ahead and expands behind. During the journey, you exist in a bubble of normal space-time, disconnected from the rest of the universe. Time inside the bubble passes normally. You can eat, sleep, work, and experience life just as you would anywhere else. There's no time dilation, no relativistic effects on your body or your clocks. Outside the bubble, space is doing something extraordinary, but inside, everything is calm. This is radically different from the experience of relativistic travel at high fractions of light speed, where time would slow down for you relative to the outside universe, and the energy of particles and radiation would increase dramatically, requiring heavy shielding. When you arrive at your destination and the warp drive deactivates, the bubble collapses gently, or at least we hope it does. You emerge back into normal space-time, now in a completely different star system. You look up and see an alien sun, perhaps a red dwarf or a binary pair of stars. Planets orbit nearby, worlds no human has ever seen. You've just accomplished something humans dreamed about for centuries, traveling between the stars in a reasonable time frame. What you do next, how you explore and interact with this new environment, would be the beginning of a new chapter in human history. Of course, this is all highly speculative. We're nowhere near building such a device, and we may never be able to, but entertaining this vision serves a purpose. It reminds us why we pursue these ideas despite the enormous obstacles. It's not just about the technical achievement, impressive as that would be. It's about expanding human presence and consciousness beyond our tiny corner of the universe. It's about satisfying that fundamental curiosity that drives us to explore. It's about ensuring the long-term survival of our species by becoming multiplanetary and eventually multistellar. If all of Earth's eggs remain in one basket, a single catastrophic event could end our story. Spreading to the stars diversifies that risk. There's also the simple fact that the universe is beautiful and fascinating, filled with wonders we've only begun to discover. Neutron stars, pulsars that spin hundreds of times per second with magnetic fields trillions of times stronger than Earth's, black holes, regions where space-time curvature becomes so extreme that not even light escapes, quasars, supermassive black holes devouring galaxies worth of matter and shining with the luminosity of trillions of suns, dark matter and dark energy, mysterious components that make up 95% of the universe, yet remain invisible and poorly understood. Exoplanets with conditions we never imagined, from hot Jupiters orbiting their stars in hours to ice worlds with subsurface oceans. Every new discovery raises new questions. Why does the universe have the properties it does? Why are the fundamental constants of nature set to the specific values that allow complex structures and life to exist? Are there other universes with different properties? What happened before the Big Bang? Or is that question even meaningful? These profound mysteries remind us how much we don't know. Faster-than-light travel would give us new tools to investigate these questions, allowing us to study extreme phenomena up close and explore a much larger sample of the universe. Even if we can't answer every question, expanding the scope of our observations would undoubtedly deepen our understanding. Let's discuss the connection between warp drives and our understanding of consciousness and intelligence. We are, as far as we know, the only species that contemplates traveling to other stars. Other animals on Earth are intelligent in various ways, but none of them build telescopes or write equations describing space-time curvature. Consciousness, whatever it is and however it arises from the physical processes in our brains, gives us the ability to imagine possibilities that don't yet exist and then work to make them real. This is extraordinary when you think about it. We're made of the same quarks, electrons, and other particles as rocks and rivers, yet we can ponder the nature of reality itself. If consciousness and intelligence are rare in the universe, then we have a special responsibility to preserve and expand them. Every human mind is a unique configuration of matter capable of experiencing wonder, love, curiosity, and creativity. Every time someone looks at the stars and asks what's out there, they're participating in something profound. If we develop the capability for interstellar travel, we'll be able to carry consciousness to places it might never otherwise reach. We might encounter other intelligences, other forms of consciousness that arose independently. The exchange of ideas between different civilizations, if it ever happens, would be the most significant conversation in history. On the other hand, if intelligence is common in the universe, then our development of warp drives might allow us to join a galactic community. Perhaps there are civilizations out there, some much older than ours, that have already solved these problems. Maybe they're waiting for us to reach a certain level of technological and ethical maturity before making contact. This is pure speculation, but it's interesting to consider. The universe is so vast and old that if interstellar travel is possible, somebody somewhere might have achieved it already. The fact that we haven't seen obvious evidence of this is puzzling, though there are many potential explanations. Maybe advanced civilizations are rare, or they avoid contact with less developed species, or they exist but are too far away for us to have detected them yet. Maybe they use communication methods we haven't thought to look for. Maybe they've transcended physical existence in ways we can't imagine, becoming something post-biological that doesn't need or want to travel between stars. Or maybe, more soberly, interstellar travel really is impossible and every civilization that arises remains forever confined to its home system. We don't know, but searching for answers is part of what makes us human. There's something deeply moving about the human quest for knowledge and exploration. We're a young species, only about 300,000 years old in our modern form. For most of that time, we lived in small groups, hunting and gathering, surviving in an often hostile environment. Agriculture began only about 12,000 years ago. Cities and civilizations emerged just a few thousand years ago. Science as we know it is only a few centuries old, and space travel is barely 60 years old. In cosmic terms, we've just been born. We're infants, taking our first steps into a vast universe. Yet in that brief time, we've accomplished extraordinary things. We've figured out how the universe began, how stars and planets form, how life evolves, how atoms work, how to cure diseases, how to communicate instantly across the globe, how to fly, and how to leave our planet. We've written symphonies and poetry, created art and literature, built magnificent structures, and decoded the human genome. We've looked billions of light years into space and fractions of a second after the Big Bang. We've sent our artifacts to the edge of the solar system and beyond. Voyager 1, launched in 1977, is now more than 24 billion kilometers from Earth in interstellar space, carrying a golden record with sounds and images from Earth as a message to any civilization that might find it someday. That golden record represents hope. Hope that we're not alone. Hope that intelligence and consciousness matter in the universe. Hope that our messages might be found and understood. The fact that we sent it, knowing the odds are overwhelmingly against it ever being found, says something beautiful about human nature. We reach out into the darkness, not knowing if anyone is there, but hoping nonetheless. This same spirit drives our efforts to develop technologies like warp drives. We don't know if they're possible, but we're going to try because that's what explorers do. We push boundaries, we ask difficult questions, and we refuse to accept that anything is impossible until we've exhausted every avenue of inquiry. If you're curious about just how challenging interstellar travel really is with our current technology, I'd love for you to check out my video called "How Long Would It Take Us to Travel 1 Light Year Nowadays?" It'll give you a fascinating perspective on the incredible distances involved and why breakthroughs like warp drives would be so revolutionary for humanity's future among the stars. See you there.